Hello everyone. In one of the previous videos, we solved the question binary search, and I said that in the next video we will be solving a variation of it. So here we are. In this video, we'll be tackling the approach to the problem search in a rotated sorted array. Now there are two keywords here, rotated and sorted. You don't need to go through all of this. I'll explain that shortly. The basics of it is just that we've been given an array and it is sorted in a rotated way. What does that mean? That simply means that if we have an array like this one over here, it is completely sorted, right? This is kind of the array that we encountered in our binary search question. In this video, we are rotating this array. Rotating means that the positions have been shifted by a certain index, right? So for example, if I had to shift this array's elements by 4 places, I would get something like this. Oh, sorry for the bad line. Something like this. So 0 would shift 1, 2, 3, 4 places, and so would all the other elements. So where would the elements at the very end go? They would shift one by one to the beginning. Alright, so the last 4 elements come up to here in such a manner. That is what this rotation implies in our array. So we have a rotated array, and now we have to search for a certain element. So if we have to search for a certain element, which could be, let's say, 7, we have to basically find out the index of that, similar to what we faced in binary search. And that is what we're going for over here. If we are not able to find our element, we have to return -1. So the question is, if we have a sorted array, an array that is sorted in some way or the other, shouldn't we try to implement binary search, especially now that we know how to implement binary search? And if you don't, I suggest you go watch that video. Now that we know how to implement binary search, shouldn't we try to reduce our problem statement such that it becomes a binary search problem? And then we solve it based on that logic, which is simple enough for us now. I think that's what we should go for. So how do we go about it? So we have to first figure out the pivot element. The pivot element is the element from which this array actually starts. And this pivot element is basically this one over here. So this is going to be our pivot element, all right, because the very last element is right before that and the array starts from after this element. So this is what we consider the pivot element. So we start off by trying to find the pivot element. This is the first step of the process. So how do we go about that? I say that why don't we take a page from the book that was binary search and try to implement some of that logic over here. How do we go about that? We will define our lower search bound as 0, our upper search bound as the last element, which will in this case be 1, 0, 1, 2, 3, 4, 5, and 6. Let's just write the indexes down just to be clear enough. And when we have our low and high, let's go in a loop. Let's keep on checking using a while loop. While this lower bound is less than the upper bound, what do we keep checking? We check for a middle element. This middle element will be like what we did previously, low plus high divided by 2. Alright, so what does that make it in this case? Let's keep on writing the values so that we keep on dry running. So we have 0 plus 6 divided by 2, that is 3. So this becomes our middle element, okay? So let's make 7 to be our middle element for now. And here, what we have to do is you have to check if this middle element is less than the element and the upper bound. So whatever is the very end of our search range, if our middle element is less than that particular element, that would imply that our pivot element has to be either in the first half. So we just write that down. Either the pivot is in first half or it is the mid element itself. Why do I say that? That is because the middle element, if it is less than whatever is at the very end of our search range. So you have to understand that this array would then mean that the middle element is part of the sorted array, right? That would imply the middle element is part of the sorted array, like this part over here. So if let's say the middle element is this one, for example, that would mean that the pivot element could either be this element itself because it is less than high and we haven't ruled it out yet, or it is less than what we have over here. Alright, so that is what it implies. So we will simply lower our search range and make the upper bound to mid. Then we check for the other case. The inverse of this is if this middle element is greater than or equal to the higher element, that would mean that the pivot is in the second half. So let's just put an else condition over here because that just fits. So else we turn our low to be ahead of the midpoint. Alright, so that would be this case in particular. So we know that this middle element, that is 7, it is not less than 2. So we don't check this. So what will end up happening is that the lower bound will shift to the next element of mid. So mid has now become 3. So that also kind of fits, right? Because the pivot element is ahead. So we reduce the search range to this part now. And as you can see, we are going in the right direction. So if this fits, we keep on continuing our loop. Let's just put that in the frame. Maybe zoom out a little. Yeah, okay. A little better. So we keep on doing this, and when will we actually stop the process? So let's just dry run this part. So we check this again. Is our lower element, which is now at what? Index 4. If it is less than high, which is true, 4 is still less than 6, the middle element will be 4 plus 6 divided by 2. That is 10 divided by 2, which is 5. Alright. So we have this 5 over here. So we check, does the element at index 5, which is 1, this is our midpoint, right? If the element at index 5, is it less than the element at the end of our search range? The answer is true because 1 is less than 2. So now we know that anything beyond this midpoint is not a part of our answer. That's not basically the pivot element. The pivot element has to be less than this, right? It can't be greater because pivot element is the smallest element in the array, right? So we have to come closer to that side. So high becomes mid, which basically means high now becomes index 5. Sorry, that was low, my bad. High becomes index 5. And we don't need to go for the else condition. We simply go back up. Is low still less than high? The answer is yes, it is. So 4 is less than 5. That would make our midpoint as 4 plus 5 divided by 2. 9 by 2 is 4.5. We round it down. Integer division. That would make it as 4. Mid is 4. Is the element at this point, this one, is it less than the element at the highest point of our search range? That is 1. Is 0 less than 1? Yes. So high, this one, index 5, becomes mid. So we reduce it, turn it to 4. We go back up, check, is low still less than high? The answer is no. 4 is not less than 4. They are equal now. So we exit this loop. So you notice that at the end of this process, low will be equal to high, and that will be our pivot element. So in case you haven't noticed till now, 4 is where our pivot element actually is. We've already marked it, right? So we've got this now. So question is, now that we have found our pivot element, how do we still proceed to make it a binary search problem? That brings me to the next step. That is, we reduce our search range. We reduce the search range. How do we reduce it? By some simple conditions. So first, let me just bring this array down. All right. So now we know that the pivot element is found at index 4. So if it is found at index 4, we need to reduce the search range. We will check if our pivot element is equal to the target, then problem solved. We simply return the pivot element. Not the element, the index, right, which was 4. But if that is not the case, we have to check which part of the array do we need to search in. So we have roughly two parts, right? If it is not the pivot element, we are left with two parts. There is this part over here, then there is this part over here. Now, one thing you must notice in both of these parts is that they are both independently sorted. This part is sorted in itself, this part is sorted in itself. And I say that our answer can only be found in one of these parts, obviously, right? It will either be on this side of the pivot or that side of the pivot, right? So if that is sorted, we need to decide which should we search in, and then we will perform binary search on that part. So before we come to the binary search part, we will simply reduce the problem by saying that, by checking if our pivot element, if it is less than target and if our target is less than the last element of our search range, this implies that the target is between the pivot and the end of this array. What do I mean by high? Let's reinitialize those values before we start this process. Something I should have told earlier, but better late than never. We define low as 0, high as again the last element. So we check, does our pivot element equal the target? That is not true. So we check if our pivot element is less than the target, pivot element is less than target, that is true. And our target, is it less than the last element over here at index 6? That is not true. 7, which is our target, is not less than 2. But if it was, what would we have done? That would have implied that the target lies in this range, right? If the pivot, if it would have been less than the target, and if the target would have been less than this element over here, it would have been somewhere in this range. But that is not the case. We'll come to that case. Before that, if it was in this case, we have to bring up our search range up till here, right? So the high range, the upper bound would have been fine, the lower bound would have been brought up to pivot plus 1. So the question is, if this is not the case, we are only left with one range, right? If it is not the pivot element, if it is not this, then we can simply move our upper bound to the highest point of this particular range, which would be high is equal to pivot minus 1. It is right before the pivot that this range ends, right? This part. So this is what we have to encounter over here. That would make our higher bound to element at index 3. Alright, so we have reduced our search range. We've said that we will search between indexes 0 and 3. That is where our answer is. And you know where the answer is, so you know that we are going in the right direction now. So lastly, we perform binary search on this. So let me just copy this and bring it down. So we perform binary search on this range. That is what we've finalized, right? So our low is 0, high is equal to 3. And I've already covered binary search in the previous video. I suggest you go watch that and you will understand how it works. I will quickly dry run this in this video just so that you are not out of the loop when you are watching this one. So we have low and high, and we start by keeping a while loop in place. While low is less than or equal to high, we will get our midpoint. That will be low plus high divided by 2. in which case our mid would be 0 plus 3 divided by 2, that is 1.5. We round it down to index 1. So this is our mid. So if element at mid is equal to the target, we simply return this element over here. But if it is not, then we have to check if, let's bring this back into the frame. Yeah. If this middle element is less than the target, which happens to be true in this case, let's see. Middle element is 5, it is less than the target, yes. So we will have to reduce our search range even further. So we've checked till mid, we know that our answer is not before mid, so we will reduce our search range and only search in this part now, that is indexes 2 and 3. How do we write that down over here? We will redefine low as mid plus 1. But if our mid happens to be less than the target, which can be simplified in an else condition, we don't need to write the entire thing down, then high will become mid minus 1. In this case, this is the condition that is satisfying. That is, our element, mid element is less than the target. So the value of low will be mid plus 1. So low was 0. It becomes 1 plus 1, that is 2. Right? So we check again. We loop it. Yeah, that's better. We loop it. We check, is low less than high? Yes, it is. The midpoint would then be 2 plus 3, 5 divided by 2. 2.5 rounded down becomes 2. Alright. So does the element at index 2, that is 6, is it equal to the target? No. Is it less than the target? Yes, it is. So low then becomes mid plus 1. Mid was 2. It becomes 2 plus 1, that is 3. So is low less than or equal to high? Well, technically it is equal to high. So we continue in this loop. So mid then becomes 3 plus 3 divided by 2, that is simply 3. Basic mathematics. So if the element at the midpoint, that is this one over here, is it equal to the target? Yes, it is. We have reached our target. We simply return this midpoint. Alright. So in one of the previous videos on binary search, I have already performed a dry run on a case where we do not find the element. If that is the case, you can just go and watch that video. You'll see how that condition works. That is how I want to wrap up this video. In the next video, we will code this entire problem up with all the 3 steps. Those were, to summarize, first we find the pivot element, then we reduce the search range so that we know which part to perform binary search on, then we actually perform binary search on that part and find our answer. Alright, so I'll see you in that video. We'll do the entire solution, and so I suggest that you stay tuned and follow for more.